Why are Fibonacci sequences so complex from simple math? Imagine a sequence that starts with just 0 and 1, and each new number is the sum of the two before it. Sounds straightforward, right? But this simple rule creates a sequence full of surprises and deep connections. The reason it gets so complex is because of how the sequence is built. It follows a pattern called a linear recurrence relation, meaning each term depends on previous terms in a fixed way. Even with this simplicity, the sequence links to many parts of mathematics and nature. For example, there is a special formula called Benet's formula that tells you the exact Fibonacci number using powers of the golden ratio, which is about 1.618. This connects the sequence to irrational numbers and continuous math, making it much richer than it looks. The golden ratio itself solves a quadratic equation and appears in the ratio of consecutive Fibonacci numbers as the sequence grows. This introduces algebraic structures and irrational numbers into the sequence, adding layers of complexity. Fibonacci numbers also show interesting patterns in their factors, their relationship to prime numbers, and how they appear in natural shapes like shells, leaves, and even galaxies. From the perspective of number sequences and series, the Fibonacci sequence is a perfect example of how a simple rule can produce a sequence with many intricate properties. It can be extended to negative numbers and real numbers using generalized formulas. It relates to continued fractions, combinatorics, and matrix algebra. Plus, it shows up in fields like computer programming, financial calculations, and biological growth. For example, some scoring systems use Fibonacci numbers to prioritize tasks or assess risks because of their balanced growth pattern. All these connections show how a basic addition rule can lead to a web of fascinating phenomena, linking simple math to complex natural and mathematical worlds.